Perfect. Oh, we don't need to record yet. Time. Okay, cool.
Great, thanks.
So thanks everybody for coming to the last session of the proof complexity workshop. So we're excited to have two experts in their respective areas. So we're going to have two talks in this session, one by Rahul Santhanam on connections with proof complexity and meta complexity, and one by Profesh Kathari on connections between proof complexity and sum of squares, and in particular, like spectral refutation algorithms. So both of these authors are experts. They've both done both been responsible for some of the main breakthroughs in both of these areas over the past decade or so. And so we're really excited to hear both of them speak. And also at the end of the session, stick around because Susanna will be going over a nice open problem list that we've gathered from everybody to help try and orient future work, I guess we could say. So Rahul, if you're ready, feel free to take it away.
Thanks a lot. Thanks for the invitation to speak. So my talk is basically on the difficulty of analyzing propositional proof complexity. So that's a question that we're interested in here. And so to start off with, just a slide about motivation, broadly speaking. Most of us are interested in complexity theory. One of the main reasons we believe in complexity conjectures, such as NP in order to P or circuit low bounds, or NP in order to co-NP, which is the main problem of propositional proof complexity, is that there are very different algorithmic approaches that we've tried to hard problems, such as satisfiability, to NP hard problems. And all of these different algorithmic approaches have failed. And that suggests to us that there's some sort of fundamental hardness phenomenon at work. The fact that we've tried very, very different hard algorithmic approaches and none of them seem to work. That seems to give evidence that there is a separation between the classes that we're considering. And I'd like to suggest that in a similar way, complexity theory has been trying to show low bounds for a very, very long time, for well over 5 decades, and very different approaches to proving complexity conjectures have failed. And perhaps we should at least investigate whether there's some sort of fundamental meta-mathematical hardness phenomenon at work in a similar way here. Just from the fact that combinatorial, algebraic, logical, topological, doesn't seem to matter what kind of approach you try, it doesn't seem to make much headway on most of our fundamental questions. And this meta-mathematical perspective has been investigated in the context of circuit complexity low bounds, via barrier results, such as for relativization or natural proofs, but not so much for proof complexity low bounds. So this workshop's on proof complexity, and one of the main sort of goals of proof complexity is to show low bounds for interesting proof systems. And that's a goal that remains out of reach for most of the proof systems we're interested in, but we don't have very satisfactory explanation for this. And there's been some recent works that try to address this gap, and I'll be discussing 2 of them mostly. So just to make this talk a bit more self-contained, even though many of you are very familiar with proof complexity, let me just have a slide on what proof complexity is, and I'm going to define it slightly differently than others have in previous talks. So propositional proof complexity studies the power of propositional proof systems, abbreviated as PPSs, to prove propositional tautologies. And what is a PPS? So for the purpose of this talk, a PPS will just be a polynomial time computable binary relation. So it's typically defined as a function mapping strings onto tautologies, but I prefer in this talk to model it as a binary relation, such that there exists y such R of phi y holes if and only if phi isn't taut. So the if and only if captures the soundness and the completeness of proof systems. So the if phi is a tautology, there exists a y, a proof. So that's the completeness part. And if there's a proof, then phi is a tautology, that's a soundness part. So this is capturing the soundness and completeness of proof systems. And the fact that R is polynomial time computable captures the efficiency of the proof system. And the nice thing about this way of looking at things is that you can easily generalize it to non-uniform PPSs just by making R poly-size computable rather than poly-time computable. This isn't something that's considered much in proof complexity, non-uniform PPSs, but they have been defined and studied, and they will feature in a couple of the results that I mentioned. So given R, and R proof of a tautology phi is a string Y such that R of phi Y holds. And we're interested in the smallest such string. So the R proof size of phi is the smallest size of an R proof of phi. And we are interested in studying for various propositional proof systems R and for natural families of tautology phi n, how the proof size with respect to the proof system R grows with the size of the formula. So we look at the number of bits required to encode the tautology phi n, and we look at the number of bits required to encode the proof, and we look at how the proof size grows with the size of the formula. The sort of classic result of Cook and Reckhow says that NP not equal to co-NP is sort of equivalent to the fact that every propositional proof system has hard formulas, a hard sequence of formulas for which the proof size grows super-polynomially. And similarly, NP not co-NP slash poly corresponds to every non-uniform propositional proof system having a sequence of hard formulas for which the proof size grows super-polynomially. So what is known about proof complexity low bounds? Super-polynomial low bounds are known only for relatively weak propositional proof systems. There's a classic work of Haken which shows low bounds on resolution proofs of the pigeonhole principle. And Iddo showed low bounds on constant depth Frege proofs of the pigeonhole principle. And there's been a lot of very interesting work kind of refining these results, improving parameters, considering other related proof systems. There's a lot of work on proof systems such as polynomial calculus, no-Schlieren-Satz, Scherrelli-Adams, for example. But despite much effort, no non-trivial low bounds are known for systems such as Frege or extended Frege, which are sort of like canonical systems. And even for the proof system AC0 parity Frege, where the lines are AC0 parity circuits, there are no super-polynomial low bounds known, even though the corresponding circuit class we've known low bounds for a very long time. So on the one hand, proof complexity low bounds have historically been harder to show than circuit complexity low bounds. So for example, circuit complexity low bounds for AC0 were shown already in the early 80s, but it was mid-90s, early 90s, mid-90s before AC0 Frege low bounds were shown. And as I just mentioned, low bounds against AC0 parity circuits have been known for a very long time, but we still don't know any low bounds against AC0 parity Frege. So proof complexity low bounds seem hard, or at least as hard as circuit complexity low bounds. But there hasn't really been any work on formally justifying this difficulty. I'm trying to understand why these low bounds are hard to show. While the corresponding work has been done for circuit complexity, via relativization, natural proofs, etc. So the question we are looking at mostly in this talk is, are there tautologies which we believe to be hard, but for which it's hard to prove that they're hard? So candidate hard tautologies for which proving that these tautologies are hard is itself hard. So which tautologies are believed to be hard? What kinds of candidate tautologies are interesting to consider? Well, ideally we'd like tautologies that are polynomial time constructible. And if we're very, very ambitious, then we'd like tautologies that can be constructed by polynomial time algorithms, such that these tautologies are hard for every propositional proof system. So those would be ideal hard tautologies, where it doesn't matter which proof system you consider, these tautologies are still hard. But this is inherently impossible because given any polynomial time constructible sequence of tautologies, you can just define a propositional proof system which computes the sequence for itself using the polynomial time constructibility and accepts all such tautologies with small proofs. So it's just not true that there is a sequence of polynomial time constructible tautologies which is hard for every propositional proof system. So what if we want somehow to get our hands on tautologies that are hard for every proof systems? We can still hope to do it, except that we need to use randomness. We can't hope to do it deterministically and efficiently. And there are a couple of candidate hard distributions which have been looked at and studied. So there's a random KDNFs with delta n clauses for large enough constants delta. So this is these kinds of formulas have been analyzed for resolution and for other proof systems. And there's random circuit low bound tautologies expressing that a random Boolean function does not have small Boolean circuits. Here I'm somewhat abusing notation language because so if you generate a random Boolean function and then write a formula saying that this Boolean function doesn't have small Boolean circuits, it's not always going to be a tautology, because with some small probability, you're going to generate a function that is easy. But just for the sake of convenience, I'm going to call these random circuit low bound tautologies. They're tautologies with very high probability when you generate formulas in this way. So these also have been considered, especially in work on metamathematics of circuit complexity by Rasparov and others. Okay, so here we're interested in metamathematics of proof complexity. Our general goal is for candidate hard distributions, we want to formalize and study the question of whether proof complexity low bounds for formulas sampled from these hard distributions are themselves hard to show. And our results will be along these lines. So as I said before, I'm going to be discussing two papers. One like paper one with Jan Pich and the other one with Iddo Tzameret. So let me discuss the one with Jan first. So the way I'm going to do this, because the actual results are a little bit technical to state, is to start off with a somewhat informal statement to try to give you the high-level intuition of what's going on, and then almost like a template of the statement, and then try to fill it in later after explaining how things are formalized. So what's the idea here? Here, as I said, we're interested in certain families of candidate hard instances. Just in this slide, candidate hard instances would mean random circuit low bound tautologies. And we prove a conditional result and an unconditional result about these hard instances. The conditional result is that if these instances are hard, so we require quite a strong hardness hypothesis, namely that these instances are hard for every non-uniform proposition proof system. And ideally, if you're trying to prove something about hardness proof complexity low bounds, you want it to be for proof complexity low bounds formulas that you do believe to be hard. So the assumption is just saying that these hard instances are indeed very hard. But if that's the case, then there is a propositional proof system R for which proof size low bounds for R are hard to prove. And they're hard to prove by any non-uniform proposition proof system. So this this hardness here is quite significant. So assuming this the hardness of these instances, there is a propositional proof system R which is hard to analyze. That's the model of this conditional result. And this conditional result can be used to derive an unconditional result. But the unconditional result now isn't for a uniform PPS, but for a non-uniform PPS. And it says that there is a non-uniform PPS for which R proof size, low bounds, and candidate hard instances are themselves hard to prove for every non-uniform PPS. So it's a completely unconditional result about the hardness of analyzing the propositional proof system R. And it's just given these templates, it shouldn't be too hard to see how to derive the unconditional result from the conditional result. It's by a sort of win-win argument. So if the assumption of the conditional result holds, so if indeed these hard instances are hard, then from the conclusion, what we want here follows. But if the assumption is false, if it is the case that there's some non-uniform PPSR for which these instances are easy, then yeah, because instances are actually easy for this PPSR, low bound proofs don't exist for R. And hence the conclusion kind of holds trivially. I mean, the R proof size low bounds will be hard to prove just because they're false. And just by the soundness of the system, it will follow from that. So yeah, it might seem like a bit of a cheat, and it's sort of a non-constructive argument, but you do get an unconditional result from conditional result of this form. Okay, so that's just a template of the results themselves. But let me say a little bit about how these templates are filled in and how things are formalized. So first of all, about circuit low bound tautologies. So what's a circuit low bound tautology? As I said, it's just expressing, it's propositional tautology expressing that for all circuits C of size S, C does not compute F, where F is a given Boolean function. And it's not hard to see how it expresses it as a DNF of size that's slightly larger than 2 to the n, assuming S is fairly small. I mean, this is like a co-NP statement, and so you can express it as a propositional tautology. And random circular low bound tautologies just means that these F's are sampled completely, uniformly at random. And S is chosen to be some large enough polynomial in N. So we talked about candidate hard instances. So there's actually a conjecture in the literature which says that these random circular low bound tautologies are hard for every non-uniform proof system. That's what Rudich conjectured. And this is what the formal statement of Rudich's conjecture looks like. There's some integer d such that for every non-uniform PPSR, when you choose f uniformly from n-bit Boolean functions, tt of f n to the d doesn't have small r proofs, doesn't have poly-size r proofs. And finally, we need to formalize what metamathematics of proof complexity means. How do we formalize a notion that a complexity low bound, a proof complexity low bound is itself hard to prove? Well, I mean, it's natural to do that again using propositional proof systems. By just saying the proof complexity low bound, you can formulate that as a tautology, and that is itself provable or unprovable in some PPS. And indeed, known proof complexity low bounds, just those for resolution and for constant depth Frege, they're known to have short proofs in extended Frege proof system and appropriately formalized. And this has been known for quite a long time. So given a PPSR, the formula R proof low bound of phi p just expresses that there's no proof of size at most t in R for phi. And that again is a co-NP statement. For all proofs, they're not valid R proofs of phi if they're of size less than t. And that can be expressed as a propositional tautology. And a similar formalization works for non-uniform PPSs. So this is fairly straightforward to do. And once you do that, then you can kind of state these results that I mentioned earlier formally. If Rudich's conjecture holds, a conjecture has been considered in the literature, then you get that, yeah, there is a propositional proof system R that's hard to analyze in the sense that no other system Q, even one that depends on R and one that's non-uniform, can show super-polynomial low bounds on R for these formulas, for these random circular low bound formulas. And we're also able to get such a result for random DNFs that there is, if this conjecture holds, there's a PPS such that for every non-uniform PPS Q, Q is unable to analyze R and to prove super-polynomial low bounds on R. So these are the conditional results. And then, as I mentioned before, you can get an unconditional result out of theorem 1 just by win-win argument. And you can get that there is a non-uniform PPSR such that for every non-uniform PPS Q, Q is kind of unable to analyze R doesn't have poly-size Q proofs. And at first, the unconditionality of this might seem surprising because this itself seems like a proof complexity low bound. These formulas here don't have poly-size Q proofs. And this is an unconditional result. So that works for every non-uniform PPS. I mean, so why doesn't that show, say, the co-NP is not an NP/poly or something strong like that? Well, the reason is that we don't know for sure that these are tautologies. So we believe that these are tautologies, that these formulas are hard for R by Rudich's conjecture, but we don't know them for sure. And that's the reason why this doesn't contradict any, this doesn't imply a breakthrough in complexity theory, but it just says something interesting about the analyzability of R. Okay, so I'd like to kind of step back and give maybe a few slides of kind of perspective on these kinds of results on the metamathematics of proof complexity, because several of you might be more familiar with metamathematics of circuit complexity, the natural proofs, for example, than you are with this setting, and perhaps it'll make it easier to appreciate what's going on here if we compare. So there are a few very direct connections between circuit complexity and proof complexity. Robert talked earlier about lifting, so that gives some very interesting connections, but between strong proof systems and strong circuit classes, there are very few direct connections. There's a rough analogy between proving circuit low bounds for a circuit class C and proof complexity low bounds for the system C Frege, where lines the proof of circuits from C. And indeed, some of the best proof complexity low bounds, example for constant depth Frege, are inspired by circuit low bound techniques for the corresponding class C. So you can think really of these theorems 1 and 3 that I mentioned here as analogs of the natural proofs barrier for proof complexity. In order to see how they're analogs, perhaps a sort of table might help. It sort of gives a comparison between them. So what is a natural proofs barrier? Natural proofs barrier rules out efficient algorithms for certifying the hardness of random Boolean functions, right? So it says that there's no efficient algorithm which certifies for most Boolean functions that they're hard, and of course doesn't falsely certify that any Boolean function is hard, and it does, and this holds under some cryptographic conjecture. It's conditional on the existence of one-way functions. And the really nice thing about this is that it applies even to very restricted circuit classes, just TZ0. There are no efficient algorithms even for certifying that random Boolean functions don't have small TC0 circuits, given an appropriate cryptographic conjecture. So what about our results? Well, our results, instead of ruling out efficient algorithms, rule out efficient proofs. So they're doing something morally stronger. So they rule out efficient proofs for hardness of random tautologies. And unlike the natural proofs barrier, they're unconditional. But the major drawback compared to natural proofs barrier is that these results only apply to very strong proof systems. Our unconditional result is even non-constructive, and we can't even put our hands on a specific proof system to which it applies. Our conditional result is more constructive, but even then, it doesn't quite apply to systems such as extended Frege or Frege, which are the ones that we are really interested in analyzing. We might not be interested in analyzing much stronger proof systems. So hopefully that at least clarifies how this relates to earlier kind of work on metamathematics of circuit complexity. And another perspective that might be somewhat useful is an analogy of Gödel's theorem. So you are surely aware of Gödel's incompleteness theorems. The first one saying that any strong enough consistent theorem system of arithmetic is incomplete. Namely, there's a statement phi, such that neither phi nor its negation can be proved within the system. The second incompleteness theorem saying that no strong enough consistent system of arithmetic can prove its own consistency. So these are kind of classic results. And one can ask whether they're analogs of Gödel's theorem in the finitistic setting of propositional proof complexity. So in a sense, we might be interested in quite fine-grained versions of Gödel's theorems in a finite tree setting. Well, at least for the second incompleteness theorem, the natural analog doesn't hold, because any strong enough PPSR has efficient proofs of its kind of reflection principle. So it can prove that R does not prove a contradiction within n steps, for example, and that was shown by Pudelak. But for the first incompleteness theorem, we can hope to establish an analog. A natural analog would be for any PPSR, there are a sequence of tautologies which don't have efficient R proofs. And this is, of course, the major low bound problem of propositional proof complexity. This implies NP in order to co-NP. And we're interested in specific propositional proof systems R to show that super-polynomial size proofs are required. And if you look at the proof of Gödel's theorem, I mean, it uses the liar paradox as kind of the motivation. The self-referential sentence that this sentence does not have an R proof. And it shows that this sentence is itself R unprovable. And Harvey Friedman first, and then Pavel Pudelak explored how to finitize the proof of Gödel's first incompleteness theorem. And they're able to do it, but the issue is that they get tautologies of size n, and they get low bounds for those tautologies. But the low bounds are actually smaller than the size of tautology itself. So they get the number of steps required in proof systems is at least n to the epsilon for some epsilon greater than 0. And this can be made quite close to n, actually. So it doesn't give us anything that we'd be interested in terms of approaching super-polynomial low bounds. So just to compare like the results that I mentioned earlier, the theorems 1 and 3, well, the proof of Gödel's theorem uses a sort of self-referential sentence, which says that the sentence says that it does not have an R proof. And that sentence is true. It does not have an R proof, and shows, and because it's true, the sentence is R unprovable. What we do is, I mean, so the self-referentiality is absent now, but instead we consider sort of like iteration of the R unprovability operator in a similar way. So for random tautologies phi, we look at the formula which says phi doesn't have efficient R proofs. And we show that that formula itself doesn't have efficient R proofs, or even efficient Q proofs for arbitrary non-uniform PPSQ. So just by iterating the unprovability sort of operator, we get sort of an unconditional result. And this looks like it might be even stronger than R unprovability, but it isn't, because it's not clear that the corresponding statements, these statements here, phi doesn't have efficient R proofs. It's not clear that these statements are indeed tautologies. They don't have to be. While in Gödel's theorem, the statement is, of course, a tautology, because that's is sort of means the same as it being unprovable. Okay, so something that is sort of a natural question is it true in general that when you have a strong propositional proof system, that R finds it hard to analyze itself, in the sense that couldn't you expect extended Frege, for example, to be able to show low bounds for extended Frege? Like if there's a sequence of formulas which are hard for extended Frege, can we expect a proof in extended Frege itself of that fact? One might guess not, and that's something that I explored in the second paper that I mentioned, with Iddo's Tzameret. We define a hypothesis called the iterated low bounds hypothesis. And what we do is, given a propositional proof system R and a formula phi that is hard for R, a constant size formula that's hard for R, we define iterated low bound formulas by just iterating the low bound operator. So the low bound operator just transforms one formula into another, which expresses that the first formula doesn't have short proofs in R. So start off with the formula phi, and then the formula phi n plus 1 just expresses that phi n doesn't have polynomial size proofs in R. And we consider this hypothesis that for any reasonable strong enough PPSR satisfying some conditions, the sequence of formulas phi n is a sequence of hard tautologies for R. So what we're trying to do here is we kind of not able to use sort of self-referentialities in Gödel's theorem to get interesting consequences, but instead perhaps iterating the low bound operator kind of helps to get hardness automatically. And it turns out that this hypothesis does hold for resolution. This follows from the exciting recent work on non-automatability by Atzerias and Muller, and all the follow-up work by Garlick and others. And we also show that it holds for strong proof systems when you apply iterations a constant number of times. So this is sort of like candidate hard distributions for formulas. For a given proof system R, it gives you some candidate sequence of formulas that might be hard for R. But I'm not going to bet on the truth of this hypothesis. It would be very interesting to try to refute it, I think, and might even be possible. And where we use this is to understand the ideal proof system of Grotjahn-Petassi. This came up yesterday. So it's an algebraic proof system where the proofs are algebraic circuits witnessing the set of polynomial equations is not common zero. And it's very interesting because it kind of connects with circuit complexity in an interesting way. IPS proof complexity low bounds imply VNP not the VP.
I don't want to interrupt, but just to let you know, you have 5 minutes left.
Okay, sure, thanks. So what we show in this paper is that there's an explicit sequence of formulas psi n believed to be hard for IPS, believed to be hard for the ideal proof system, such that VNP not equal to VP if and only if IPS can't efficiently prove low bounds against itself for these formulas. So under the standard complexity assumption, which most of us believe in, the permanent doesn't have polynomial size arithmetic circuits, then IPS can't efficiently prove low bounds against itself for these specific formulas, psi n, which we believe to be hard. And one interesting aspect of this is that it gives you an equivalence between proof complexity low bounds and algebraic complexity low bounds. VNP not to VP is an algebraic complexity separation. And the statement about IPS not efficiently proving low bounds against itself is a proof complexity low bound. And in fact, there's nothing particularly special about IPS. The equivalence is going to work for any reasonable algebraic proof system that's at least as strong as IPS. So again, it might be useful to compare this result with the result we saw earlier. So this sort of gives like a new barrier in terms of showing proof complexity low bounds. the earlier barrier we had ruled out efficient proofs for hardness of random tautologies and was unconditional. This barrier, well, rules out efficient proofs for hardness of explicit formulas, because the formulas psi n here is an explicit sequence, polynomial time computable sequence. But it's now conditional, it's not unconditional. And it applies to a well-studied proof system that many proof complexity theorists are interested in, rather than to these strong and sometimes non-constructive proof systems that occurred in this earlier paper. Okay, so those are just kind of a couple of results and recently, but I think there's just a lot that's unknown and there's a lot of kind of scope for future work. So let me just kind of indicate a few directions. We focused on propositional proof complexity in this talk, but how about setting a bound arithmetic? In another paper with Jan Pich, we show some unprovability of strong proof of low bounds in PV. But the more interesting case is Buss's theory S12, and nothing is known so far for that theory. And I think the main open question, the one that's most interesting for me, is to get some evidence or otherwise. Well, it would be even better if we could prove extended Frege low bounds and extended Frege. But if not, maybe we can get some evidence of the intractability of these systems. Even under a strong but still believable complexity assumption, can we show that extended Frege low bounds are hard to show? That would be interesting. Third direction is that there's all this work recently by Jan Krajicek, Igor Oliver, and others on unprovability of circuit upper bounds. And it would be nice to combine that with the work that I just mentioned, that I've discussed in this talk, which is on unprovability of lower bounds. And perhaps they can kind of like meet, and we can actually get independence results for natural complexity conjectures from, say, theories of bound arithmetic that aren't too weak. And finally, there's like, technically, I didn't talk much about the techniques because I thought it was more interesting to just explain the results themselves and their motivation. But technically, this double proof complexity low bound operator, R proof low bound of R proof low bound, that the property, the truth preserving property it has, is something that comes up in both the results that I mentioned here. And I'm interested in how widespread a phenomenon this is. I mean, is it the case that for like a large class of formulas, or for any formula, and for any strong enough proof system R, that phi is true, if only if R proof low bound, if R proof low bound is phi is true? I mean, I can't rule that out, and I think that would be very, very interesting to know. Thanks.
Cool, great, thanks. Any questions?
I'll ask a little question. Can you hear me?
Yep, go for it.
Yeah. So can you say something about the result you have with Iddo showing that VP not equal VNP implies, yeah, in that direction. So one possibility, I also believe that the formulas are hard, but they might just be hard because they're satisfiable. Can you say something about that?
Yeah, absolutely.
That was my question too.
Yeah, I mean, that's definitely a possibility. So our belief that those formulas are hard is just based on an analogy of the Razborov's conjecture. So Razborov sort of conjectured that all the truth table formulas are hard for extended Frege. And one could similarly conjecture that algebraic truth table formulas, or the version or the analog algebraic complexity of truth table formulas, are hard for IPS. And if we conjecture that, then these would be tautologies. But it's possible that, maybe algebraic complexity is easier to analyze than Boolean circuit complexity, and maybe IPS can just prove that VMP not to VP. Of course, that's a possibility too, which we can't rule out.
Thanks.
Any other questions for Rahul?
I have a quick one. This is just about like almost on the first slide, you mentioned like it's not interesting to look at an explicit sequence of tautologies, which is hard for every proof system. Like, I'm wondering if you didn't define it to be tautologies, just a sequence of formulas, that it's hard for every proof system to prove all the ones that are tautologies. Like, does it become interesting in that? Because it seems like that would just be just as good way to define it.
Yeah, but I mean, it might be, but I mean, of course, one could just kind of generate a sequence of non-tautologies, and of course, they'll all be hard for every proof system. So how does that?
I guess you would want infinite. if infinitely many of them are,
Yeah,
like, it seems like
that's-
if you assume like NE is not equal to E or something, you would be able to get a sequence. I don't know. Anyways.
Yeah, no, that's possible. Yeah, I mean, it is possible that you can kind of insist that there's infinitely many in the sequence that are tautologies, and you want, all of those to be hard for every propositional proof system. I think similar things have been considered by Jan Krajicek and sort of like in trying to understand Rasborov's conjecture. Because there you're interested actually in showing that every formula from a given class is hard, not just that a random one is. So that might be somewhere to look if you're interested in other places where this has been considered.
Thanks.
Yes.
All right, awesome. So let's thank speaker again. So we can move on to the next talk. Lovely.